Hello everybody, and thank you for the opportunity. So in the volume electron microscopy community, we all know where the bottleneck lies. It's segmentation, right? So in volumeEM, data is typically collected as a stack of 2D images, which are then computationally combined into a 3D volume. In this case, I'm showing you a FibSem reconstruction of a liver cell. Now, if you want to extract and visualize a specific feature of interest from that data set, that's something that we can use segmentation for. In this particular example, I'm going to show you segmentation of mitochondria from this volumeEM data set. Specifically, we're talking about instance segmentation, where we want precise and accurate segmentation of each and every mitochondrion in this data set. And of course, we want it not just for this representative 2D image, but for the entire 3D volume. And the reason is that'll allow us to visualize the entire mitochondrial volume, but it will also allow us to do downstream quantitation and analysis, which is of course where we want the volumeEM field to go. Now, segmentation therefore is critically important, but the way most of us do it still is manually. Right? Now, manual segmentation is slow, it's error prone, it's biased, but we still do it because it's cheap, easy, and accessible. So this is something that my lab wanted to attack. And so we developed deep learning approaches to help accelerate this segmentation step. Now, there are other solutions and software solutions that, commercial software solutions that allow us to do this as well. But many of them do this in a dataset specific manner. What I mean by that is if you have a volumeEM dataset, often you're expected to segment out a subset of this volumeEM dataset to create what's called ground truth, which is then fed into an AI model. And so now the model learns, for example, what a mitochondrion is in that liver dataset, and it can get you pretty good segmentations for the entirety of that volumeEM dataset. And this works, except that now if you feed a new data set, let's say a kidney volume, to that same model, it tends to perform poorly. So you have to go back and do another round of annotation for that particular volumeEM data set. This is something that we wanted to avoid by creating a generalist deep learning model. And in this, we essentially fed a whole bunch of volumeEM data to the model that we call MitoNet, which can then learn what mitochondria are in a variety of contexts. So now if you challenge MitoNet with volumeEM datasets from a variety of volumeEM approaches or tissue contexts, it tends to perform quite well. So MitoNet is the name of our model, but the Napari plugin, which allows users to use it very easily, is called empanada. So empanada is available on Napari. And the way you can use it is quite simple. As I mentioned, MitoNet is a generalist AI model, meaning that at a click of a button, you can get instant segmentation of mitochondria in a variety of completely different and unrelated volumeEM data in 2D as well as in 3D. And the speed with which MitoNet works, by the way, all of this is in real time, means that you can now get a dramatic acceleration of segmentation in your pipelines. Most recently, we've released DropNet and NucleoNet. These are two models that are also available in the empanada plugin. You just go to the drop-down, select DropNet and hit Run Inference. You can get instant segmentation of each and every lipid droplet. Similarly, you pick NucleoNet and hit Run Inference, and you can get instant segmentation of high quality of each and every nucleus, not just in a very small number of cells, but we can now show that for things like array tomography, you can get thousands of instances of nuclei, mitochondria, and lipid droplets. So slowly but surely, we're building the capacity to get organelle segmentation for a wide variety of volumeEM data. We are stunned that more than 110,000 downloads have already occurred as of now, and we've just released Empanada version 1.2. We're really happy about this. Empanada comes not just with the ready-to-go models, but also with a whole bunch of goodies. So you can run inference on your own data in 2D or in 3D. You can also create your own models using the Empanada backbone. And there are other goodies that we have included for proofreading, etc., etc. So please go ahead, download, and give Empanada a try. It's software solutions like this that I believe CCP-volumeEM can and should support. Essentially, you want these software to be rigorously tested and benchmarked. Given that volume-EM data are getting larger and larger, CCP-volumeEM must provide tools for conversion to next generation file formats. And equally importantly, CCP-volumeEM, I really hope, will take training to a new level, not just for end users, but also for programmers and analysts. Because given the heterogeneity of volume-EM, it's unlikely that there will be a silver bullet single solution, meaning that each of the modules that are developed independently should be interoperable. And finally, just a plea to the funders. Software developers must be funded well and imaginatively. So, for example, some fraction of this person could be funded by the host institution for internal projects, whereas some other fraction could be centrally funded for community obligations. So, I urge all of us to sit together and come up with solutions that will allow for robust and resilient software solutions in the volume-EM space. And with that, I will stop and thank you for your attention.